In today's lesson, we're going to learn about antiderivatives, which is sometimes referred to as indefinite integrals. Basically, antiderivatives is the opposite of the derivative. So it's derivative in reverse is the easiest way to think about it. So for example, if you know that the derivative of some function is equal to 3x squared, then if I would say, okay, what if I wanted to figure out what was the original function I took this derivative of? So I want to find the original function. That is the antiderivative. Starting with the derivative and figuring out what the original function was. So I know, okay, well, I have x squared, so I know my original function needed to be x cubed because of the power rule. So if I have x cubed, I know I bring the power to the front and decrease the exponent by 1. And so if my function was x cubed, and then if I found the derivative of x cubed, that would give me 3x squared. So I know that x cubed is an antiderivative of 3x squared. But what if my original function was x cubed plus 5? Well, the derivative of that is also 3x squared because the derivative of a constant is 0. And this can go on forever. It could have been x cubed minus 43 because the derivative of that is also 3x squared. And because that there are so many, infinite many functions that have the exact same derivative, what we would say is that the original function, if our derivative is 3x squared, we'd say our original function is x cubed plus c. And we just let c equal to some constant, 0, 5, negative 43, negative 22, pi 1,500, whatever those numbers happen to be, just some number that could have been added that when we took the derivative of that, it became 0. So this is the actual antiderivative of my original example. Now, that's a lot to kind of say, as I had to explain what each of these notations meant. So if my original function was x cubed plus c, then my derivative is 3x squared. And so we would say that the antiderivative of 3x squared is x cubed plus c. Well, that's kind of hard to write down. So calculus came up with some notation to make this easier. And it's this right here. This is called the integral. In this integral notation, say I have the integral of 3x squared dx. So let's identify a few things here. So this right here is called the integral symbol. So that's our integral sign. The function inside the integral is called our integrand. And this dx tells us that this function was differentiated with respect to the x variable. So this tells us our variable of integration. Or it's sometimes referred to as the independent variable of the equation. So x is our independent variable. So this is our variable of integration. So I'd say the integral of 3x squared dx is equal to x cubed plus c. And that is my antiderivative or my indefinite integral. And that is the process. So this integral sign here is our direction. It tells us to find the original function whose derivative is the integrand. So let's do some examples. Let's say we're given integral of x cubed dx. So this means I want to find the function whose derivative is x cubed. So I'm going to think about how I find the derivative. Well, I found the derivative by decreasing my power by 1. So if the power ended up at 3, then I would have to add 1 to my exponent to get the original power, which was 4. And then remember, normally, if I have the derivative of x to the 4th, I take the power to the front and multiply by x to the 4th. But since I'm going, instead of taking the power to the front, I want to undo that operation. So just like here, I undid subtracting 1 by adding 1. I'm going to undo multiplying by 4 by dividing by 4. So these are going to do our inverse operations. And then tag on your plus c for any constant that might have disappeared. And so I have my antiderivative of x cubed dx is x to the 4th over 4 plus c. All right, let's find the integral of 5 dx. Well, if I have a constant, I know my original function would have to have x to the 1st power plus c, because the derivative of x to the 5th, a derivative of 5x is just 5. So that would be our integral. So what we came up with, what these examples are showing us, is we've discovered our first rule of integration. This is the power rule for integrals. So the power rule for integrals says, if you're taking the derivative of x to an n power with respect to x, the integral would be equal to x to the n plus 1 power divided by n plus 1, and then plus your constant c. So that's going to be our first rule. So let's do a few. Let's say I want to find the integral of 7x cubed dx. Well, the constant that's there just comes out, and then I'm going to do that x cubed. I'm going to use this power rule here. So that tells me I add 1 to my exponent, so 3 plus 1 gives me 4, and I divide by that 4. So my answer is going to be 7/4 x to the 4th plus c. And that is my antiderivative. Let's say I have the integral of x to the negative 3rd dx. So the same thing happens. I'm going to take my power and add 1. So negative 3 plus 1 gives me a negative 2, and divide by that new exponent plus c. So just simplifying this down, I get negative, and I have a negative exponent, so I can write it with a negative exponent plus c. That's my answer. Okay, these rules also apply for radicals. So if I want, I can also use the power rule anytime I find the integral of a radical. So let's say I wanted to find the antiderivative of x, the square root of x dx. I would first rewrite that radical as a fraction power. So this becomes the integral of x to the 1/2 dx. Then I'd use my power rule. So I would add 1 to my exponent. So 1 plus 1/2 is 3/2. And then I would divide by that new exponent. So that would give us 2/3 x to the 3/2 plus c. Would be the antiderivative of the square root of x. Let's do one more. Sometimes you can do multiple steps. So let's say I have the integral of 3x squared plus 2x minus the cube root of x plus 4, the fourth root of x cubed minus 9. And our variable of integration is dx. So first, rewrite the integral so that you have all exponents. So I'm going to replace this cube root of x as x to the 1/3. I'm going to replace this fourth root of x cubed as x to the 3/4 power. And then I'll be ready to integrate. So constant comes out. X cubed is we add 1, x squared, we add 1 to our power, so it becomes x cubed over 3. Constant comes out. With this x to the first, that's going to be the first, we add 1 to our exponent, so it becomes x squared over 2. And then here we have x to the 1/3, so 1/3 plus 1 is going to give us to the 4/3 power over 4/3 plus 4. And here we have x to the 3/4, so we add 1, so 3/4 plus 4/4 gives us 7/4 over 7/4 minus 9x plus c. So simplifying this down, the 3 and the 3 cancels out, so that gives us x cubed. The 2 and the 2 cancel out, so it becomes a positive x squared. When I divide by a fraction, I flip and multiply, so this becomes negative 3/4 x to the 4/3. Okay, I'm going to flip and multiply, so this becomes 4 times 4/7 or 16 over 7. X to the 7/4 power minus 9x plus c. All right, so now we've learned how to integrate or find the antiderivative using what's called the power rule of integration. Pause the video at this point and work in your problems 1 through 8 in the Canvas antiderivative / indefinite integral assignment. When you complete those 8 problems, come back here and push play. Okay, let's continue looking at integration. Now for these next examples, we're going to have to do some simplification first before we can actually evaluate the integral. And because of this, notice this equation is written as a quotient. We have one function divided by another function. Well, there is no quotient rule for integrals. And so I need to first simplify this integral so that I can eliminate our quotient rule. So to simplify this, I will take my x and divide that by each term. So I'm going to take that 3x squared divided by x. I'm going to take my 5x to the 4th and divide it by x. And I'm going to repeat this process for all terms. And then I'm going to simplify each fraction. So that becomes just 3x minus 5x cubed plus 9 minus 7x to the negative 1, so I can use my power rule. So I want all these x's raised to some power. Now I'm ready to integrate this, and I'm going to integrate each term using my power rule. So the constant comes out in this first term, and then I take my x and I increase my power by 1, so that becomes now a power of 2, and divide by that new power. So minus 5, this becomes x to the 4th over 4, plus 9x minus 7, and notice here, something unique happens at this problem. Let me highlight this. So we have this x to the negative 1. And if I follow my power rule notation for this, when I do this, I would end up with x to, if I take -1 plus 1, that gives me x to the 0 over 0. But that gives me a problem. I can't divide by 0. We can't do this x over 0. So I have to think back to my derivatives. And I need to think about what function gave us a derivative. So what function, when I differentiated it, the derivative was equal to 1 over x. Well, if you remember, that was our natural log of x. The natural log of x's derivative was 1 over x. And so when I have to think about that when I do this term here. So the integral of this, yeah, I can't do the power rule. The power rule doesn't make sense here. So I have a new rule now, and this is our integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So that's our we have a new rule here for integration. So let me fix this. So we saw that that did not work. And so this, when I see -7 x to the -1, that becomes -2 natural log of x, and then plus our c. Simplifying this down, I get 3/2 x squared minus 5/4 x to the 4th plus 9x minus 7, the natural log of x, plus c. And since I put that x in the absolute values, I don't have to do a qualifying here that x must be greater than 0. X can be any number as long as I just do the absolute value there and make it a positive inside our logarithm function. So that's a new rule, and that sometimes applies when we're having to do this simplifying. Let's try another example. Here we have a function times a function, but again, just like integrals do not have a quotient rule, there's no product rule for integration either. So I need to first multiply x plus 3 times x minus 4, and so that gives me an x squared minus 4 plus 3, which becomes a negative x. Whoops. Which becomes a negative x, and then minus 12. And so I'm going to integrate x squared minus x minus 12. So I have increased my power by 1, dividing by the 3. Increase my power by 1, divide by 2. Increase my power by 1, add my plus c. Do not forget your c. And that is my antiderivative. This is similar, but notice I have to do a couple steps because that square on that binomial means I have 3x minus 4 times 3x minus 4. And so I need to figure out what 3x minus 4 times 3x minus 4 is. And so that's going to give me a 9x squared minus 12x minus 12, so that's a minus 24x plus 16. And now I got to distribute the x to everything because again we don't have a product rule. So that's 9x cubed minus 24x squared plus 16x with respect to the x, dx. And so now it's in the form where I can use my power rule and I can find the integral of this. So the integral constant comes out, add 1 to my exponent, divide by my new exponent. Constant comes out, add 1 to my 2, which gives me a new exponent, it's a 3, so I must divide by 3. Add 1 to my exponent, so that's 1 plus 1 gives me 2, so I must divide by 2. Add my c. So this gives us 9/4 x to the 4th minus 8x cubed plus 8x squared plus c. And that is our antiderivative of this function. So now that we've talked about some of these ones that you have to do some simplifying before you can find the antiderivative or before you can find the integral, please pause the video and work the 9 through 11. So work all the rest of the polynomial problems, and when you come back, we'll talk about the integrals of trig functions. All right, so now we're going to have a few more rules that we need to get so we can memorize these, and we're going to do the integration of trig functions. All right, so our derivative is sine, so we got to think about what function, when I took the derivative, it gave a sine. Well, that was cosine, but actually cosine gave us negative sine, so I'm going to have to plug in a negative here. So the integral of sine of x is negative cosine of x. Now, if I put a number inside the function, that's multiplying by the x, so sine of 3x or sine of 4x or sine of 20x, that integral follows a nice pattern. It's still the same rule. We have the negative cosine of what's inside our trig function. Whoops. Which is nx. But what's going to end up is you're going to divide by that n plus the c. So that's a nice little kind of pattern to know. Works out when we're simplifying some of these trig ones. The integral of cosine of x, well, that's going to be sine of x plus c. And the integral of cosine of n to the x is going to be sine of n to the x over n plus c. Secant x tangent x, well, we know that the derivative of secant x is secant x tangent x, so the integral of secant x tangent x is secant x. And then the same thing happens here, so that's going to be secant of nx divided by n plus c. Now we know if I took cosecant and differentiate that, I get negative cosecant cotangent, so I'm missing the negative, so I got to add the negative back in. So the derivative of cosecant x cotangent is negative cosecant x plus c. And if I add a number inside the trig function, that's going to be negative cosecant of n to the x over n plus c. And then if we're going to integrate secant squared of x, is equal to tangent of x plus c. And so the integral of secant squared of n of x dx is equal to tangent of n to the x over n plus c. And we have one more I could not fit on here, so let me scroll up for the next one. And so the integral of cosecant squared x dx is equal to negative cotangent x plus c. And the integral of cosecant squared into the x dx is equal to negative cosecant of n to the x divided by n plus c. And so those are our first few trigonometric identities. Notice I didn't have on here just the integral of tangent because that one's a little bit more complex. We'll worry about that later on in the year. So these are just the trig identities that you need to know for now. And these are the basic trig integrals. So let's do a few examples. So if I wanted to find the integral of sine of 5x dx, well, I know the integral of sine is negative cosine, and so that's going to be equal to negative cosine of 5x divided by 5 plus c. That's it. You're done. Okay, I want to find the integral of secant squared x dx. Well, that's actually one of our formulas. The integral of secant squared is tangent of x plus c. Integral of cosine of pi x dx, well, that's going to be the integral of cosine is sine, so that's going to be sine of pi x over that constant pi plus c. Same thing here. We got secant of something, tangent of the same thing. So secant tangent rule is what I'm using here. And we know that's the integral of secant of x over 2 tangent x over 2 dx is equal to our secant of x over 2 over 1/2. That's our n plus c. So 1/2, if I'm multiplying by a fraction, I flip and multiply. If I'm dividing by a fraction, I flip and multiply. So my final answer would be 2 secant of x over 2 plus c. Now, just like with polynomials, sometimes when we're working with trig functions, we're going to have to do, we might do multiple steps, or we might have more than one trig function at a time, and we might have a constant out in the front. So you're going to do the same thing as what we did before. I'm going to take that constant out, and I know the integral of sine of x is negative cosine of x minus 3, and I know the integral of cosine of x is sine of x, and then so this becomes negative 4 cosine of x minus 3 sine of x plus c. Same thing here. I'm going to take my 2 out, and I have secant squared x. Well, I know the integral of secant squared x is tangent of x, and I know the derivative of cosecant squared x is negative cotangent of x. So my final answer would be 2 tangent x plus 5 cotangent x plus c. Okay, in these last couple examples, here we're given it as written as a quotient, or sometimes you'll see it written as a product. Now remember, there's no quotient rule or product rule for integration. So I need to rewrite this so I can get rid of the fraction, rid of the quotient, so I can't have my trig function in the denominator, and I got to get rid of my product. So I recall some of my trig identities. I know that secant of x is the same thing as 1 over cosine. So I could rewrite secant of x as 1 over cosine. And again, if I'm dividing by a fraction, I flip and multiply. So this original problem is the same thing as 2 cosine x. So I have to rewrite it as 2 cosine x before I can find the integral. And now I'm just going to integrate this. And I remembered that the integral of cosine is sine of x, and so I'm going to multiply that by my constant 2, so I get 2 sine of x plus c is my answer for this problem. Here I have to recall some rules of some of my trig identities. Well, I know that sine squared plus cosine squared is equivalent to 1, so this becomes, so I know that equals 1. This becomes just sine of x plus cosine of x dx. So sometimes we're going to use some of our trig identities that you learned in trig class. And so I know the integral of sine of x is negative cosine of x, and the integral of cosine is sine plus c. So sometimes on the trig you will have to do some simplifying. Just remember, in integration there's no product rule of integration and there's no quotient rule of integration. So we have to rewrite it so that we can get rid of the products or the quotients, and then we can integrate. Alright, so that concludes our antiderivative video and our integrate or our indefinite integral. That means the same thing. So I want you to go ahead and stop the video and finish up the assignment on Canvas.